Hi, welcome everybody. Every few years, technology presents an opportunity to completely reshape and transform how we build networks, run them, and operate them. And that's something that we're going to talk about today. Welcome to TLC202. My name is Robin Harwani. I lead the worldwide technology teams focused on our customers and partners within the telecommunications IBU. And with me, I have Ollie. Why don't you introduce yourself, Ollie?
Yeah, and hello, nice to meet you. I'm Olivier Simon. I'm VP of Smart Networks and Data in Orange.
Thank you, Ollie. And Iman, the visionary who started this effort within AWS.
Hi, everyone. My name is Iman Grida Benyaya, Principal AI/ML Solution Architect in the Telco IBU, in charge of the AI and network domain.
Thank you, Iman. Thank you, Ollie. So, as we go into what we're going to look at today, generative AI-powered graph for network digital twins, building smarter networks, leveraging the technologies available today, which were just not possible. If you look at an operator, a telecommunications operator that is running a worldwide network across multiple countries, such as Orange, operating in 23 countries, they have unique challenges, problems that are geographical, policy, governance, and so many different facets that they need to plan for. And what we're going to talk about today is go into this conversation, the technology collaboration that we have had with Orange over the last years, and talk about the problem set that Orange is dealing with across the world. This is by far a very, very complex network that operates across multiple countries, multiple geographies, different parts of the world, across continents. And that's something we're going to talk about, the challenges that we face there. And Oli is going to walk us through that. After that, Iman is going to walk us through the problem framing, the solution that we are looking at from a graph attentional neural networks, as well as generative AI technologies, how they come into it, and then demonstrate how all of this works for a network that has thousands and thousands of network elements across access, transport, and core networks. And that's something that's going to come up in the mobility scenario, but it can be applied to any network, fixed, enterprise, mobility, you name it. So we're looking forward to sharing what we have learned in this space and then going into the depth. Orange and AWS. Orange and AWS have been partners at least for the last 7 years that I have been at AWS. And we've had a deep partnership across Orange Business, Orange technology teams, as well as within the networks domain now over the last few years. We are collectively working towards supporting Orange and enabling Orange team for their aim to reach level 4 in terms of autonomous networks by 2025. Now, I'll share just in a little bit what that means. Solution collaboration for paths to production. We want to leverage the latest and greatest technologies when it comes to the capabilities available in the network, as well as in AWS, to bring the autonomous network vision to life. So what does autonomous network truly mean? Autonomous networks, based on the guidelines from industry bodies like TM Forum, is a level of a network where the network is able to detect, read, and make sure that there is automation within the observability, management, understanding of faults, root cause analysis, and bringing to life the failure detection and failure remediation eventually. These are stages of maturity that have been discussed in the industry, but the advent of artificial intelligence and generative AI makes it possible in conjunction with technologies like graph neural network to make this a reality. I'll hand it over to Ollie to brief us as to how they see their network, the challenges they face across these 23 countries, and how they have started the innovation with us. Ollie?
Sure. Thank you, Robin. So just a quick look about Orange for those who are not familiar with us. We are a telco operator. We are operating mobile and fixed network across 26 countries. These 26 countries are mainly in Europe and in MEA region, mostly in Africa for MEA region, plus Jordan and Egypt that are a bit aside. We have almost 300 million customers. Hopefully, we will cross the bar soon. More than 100,000 employees. And we are the 8th global telecom brand in the world. So what you need, I think, to understand about telcos, if you are not familiar, is the size of what it means in terms of the size of our network. So the first thing is that we have a lot of different equipment in different network domains like transport, core network, radio access network. We have more than 1 million piece of equipment, and we have to manage this piece of equipment. We have to understand when they are healthy and when they are unhealthy. And the complexity about it is that their profile is really different. If you consider a base station, for instance, in Paris, in a very dense city environment, and a base station that maybe in Guinea, in a rural environment, the shape of the traffic, the patterns of the traffic are clearly super different. And it means that detecting anomalies, for instance, with static methodology just does not work because the patterns are so different that you cannot do that. And this is one first reason why we need AI, because the network complexity is getting bigger and bigger, and we still need to manage this equipment, but we need clearly new methodology that can, let's say, accommodate this difference between different equipment. Another thing is the number of the volume of data and the number of type of data that we have. So just another example is what we call the call detail records. So call detail records are the way operators used to bill the customers. So at the old time of analog call, a call detail record was generated when I call Iman, for instance. At the end of the call, I had a call detail record that said, okay, you called Iman, this is your number, this is her number, and you call her for like 2 hours, maybe 2 minutes or 2 hours. I don't know. Depends on the day. And now you have call detail records for everything. When you go to the internet, when you go to Google Maps and so on, you have thousands of call detail records that are generated. And overall, for Orange, the number of call details records we have every day is more than 1,000 billions, 1 trillion, if you imagine. The volume is also huge. The cumulated volume of all the data that is generated by equipment and probes is above 1 petabyte every day. Obviously, we are not recording everything, but you can imagine that as such, it's a challenge to manage this level of data. And we have even more type of data that we are not looking at so much, like syslog and call trace record. And there is a huge potential with this data to continue to increase what we are doing with the network. And finally, we have also millions of alarms. So you can tell me why you have billions of alarms if your network works properly. The thing is that an alarm is not necessarily an incident. If just another example, if you go, if you're driving and you go to a tunnel, maybe you will have a call drop. It generates some alarms, but it's not an incident. So we also have to manage this huge volume of alarms in a way that cannot be humanly looked at. And this is, part of the project that we are doing. So just a quick look about where we are using AI. So the first area in the history where we started to use AI is about network investment. It's about the decision making of where we are putting a new site, where we are adding capacity. And in order to make this decision making correctly, you need to have a methodology to understand the way the traffic will evolve site by site and even cell by cell sometime. AI is good at doing that. You also need to have the capability to understand the way the customer will evolve. So for instance, if there is a shopping mall that will be created in 1 year, so you need to invest there. If you have enterprise that are moving, you need to change your investment plans and so on. And this is the first area where we started to use AI with very large return of investment. If you are a telco and you're not doing that, you should do that. You will, it's a matter of tens of hundreds of millions. The second area is predictive network maintenance. What does it mean? It means that we have a lot of operation to do on the network, and it could be reactive or it could be predictive. It's better to be predictive, and in order to be predictive, you need to be able to predict, and AI is very good at prediction. And here again, there is really a very large source of money that you can get. One specific area is intervention. So obviously, with these millions of equipment that are across a lot of geographies, we have a lot of people going on site to maintain this equipment, to change boards, to make operation and so on. It's about 2 billion a year for an operator like Orange, the spends that we go in this direction. And if you can avoid, let's say, useless intervention, then you have immediate benefits in your OPEX, obviously, and also in your carbon footprint. Because this is, in many countries, this is the first source of carbon footprint for operators before, sometimes, depending on the country, before the network. Network optimization, so we are not using AI only to avoid incident or to manage incident. We are also using AI to tune the network, especially the radio access network. A radio access network has thousands of parameters. So obviously, this is not something that you can, let's say, obviously you can manually do that, but you do not get the last 10 or 20% of benefits that you can get without AI, and we've started that. And finally, the network change. So it's another process. So network change means that every day we need to introduce new equipment, or we need to change some equipment, or we need to make software update and this kind of stuff. It's changing something is always a risk. And in order to manage this risk, you need to be able to kind of simulate what will happen, what could be the impact, who could be the customer impacted, is it let's say, a very high-value customer, and so you apply different procedure. And here again, doing digital twin and doing simulation is a must-have. All right, just a couple of examples of some use cases that we are doing in countries. So for the network, so on the left side, you have network operation center. This means these are the teams that are monitoring the network and managing some change remotely. And on the right side, you have field operation, which is a couple of use cases that you have here, where people have to move to the different site. So just one or two examples. Network capacity, I talked about it already with investment optimization. The project we are working on with AWS is about using graph representation of the network to do root cause analysis. We will go into details about this one. We are using AI, for instance, to manage ticketing. So ticketing is a basic process that you have everywhere on operators when you have something to do on the field, especially. And tickets, especially for incident tickets, could be really complex. It's not just like, okay, you have to go on this spot and you have to remove this board and put this board. Usually the tickets include a lot of things about the anomalies that were detected, the alarms, and so on. And a ticket could be like 20 pages. It's not like a metro ticket, you know. It's like a book sometimes. And we have started to use Gen AI to basically summarize what is important in the ticket, summarize what is important to know for the technician to do on site, and also to include, to enrich this ticket with some documentation, for instance, about the brand of the equipment or the type of equipment that needs to be touched. And let's say maybe one last example. We are also using AI for 2-3 years now to detect incident in the voice quality. So the idea of this detection is to look at time series of KPIs and to detect if there is something, let's say, unexpected in the pattern of this KPI, and this is usually a way to start investigation. Yes, and just one thing that I have not said. So we are doing that across all the geographies. Basically, France is our first country, and this is also the biggest country and where we have most of the team. So we are using France usually to start some project, but we are obviously doing that in our 26 country. So let's focus now into the discussion that we will have today, most of the discussion. So here you have a typical example of the way incidents are managed with AI for an operator like Orange. And the first step is to detect the incident. It could be obvious, but it's not obvious at all. I told you some minutes before that we have millions of alarms, so it's not just looking at, okay, there is a red button starting to flash, because you have red button flashing like it's a Christmas tree basically that you have. So the first thing is to look at the different metrics that you can collect and to detect that there is something strange or something unexpected or something unusual happening, and AI is very good to do that. When you are sure that there is something weird happening, then the second step is always the same. It's, okay, there is something weird happening, but what is the source of that? What is the equipment that is problematic, or the system that is problematic? So root cause analysis is the second step. It's clearly the step on which we concentrate the most today, because the first step now is kind of, let's say, mastered, and we are deploying that widely. Root cause analysis is a bit more complex, and Iman will talk about that. And the last step is, okay, you have detected that it is this specific equipment that needs to be fixed, but what is to be fixed? What should you do? Do you need to restart? Do you need to change the equipment? Do you need to make a software update? So this is the remediation. AI is starting to be useful here, but I would say it's kind of experimental today. Most of the remediation action that operators do today are at least confirmed by human people and usually triggered by human people. All right, so root cause analysis. So this RCA that you see everywhere means root cause analysis. So this is the second step that I have described. The way it works today is first we are using time series. So time series could be time series of KPIs, like for instance call drop rate. You monitor the number of call drop, of the ratio of call drop that you have. And you try to detect that there is something unusual. You can do that with one time series. You can combine also. Usually you need to combine with several KPIs, because in order to be sure that there is an incident, one KPI is usually not enough. And finally, you can combine that with other piece of information, like alarms, for instance. And you can also include in this investigation some what we call expert rules. So this is basically the way it works today, but there are limitations. And the first limitation that we have is these expert rules. This is the way really the operator have managed their network operation center in the history. They receive they collect a lot of data, and they apply some rules on this data. For instance, if this specific KPI crosses this threshold, and you have beside another KPI that is below this threshold, then you need to do this. And with time, they enrich these rules. They try to maintain these rules, but typically for a network operation center of Orange, you have now thousands of rules that are in place. And the problem is that it's super difficult to maintain. It's also very impacted by when you introduce a new technology, and it's very static and kind of inefficient. It takes a lot of time with this methodology to especially to make the root cause analysis. Another problem is we are using a lot correlation. So as said, we have different KPI and we can correlate them together. And with this correlation, it can help to make this root cause analysis. But the problem is that correlation is not causation. You can have a correlation between, let's say, eating chocolate and being a Nobel Prize. Probably it's not because you eat chocolate that you will be a Nobel Prize, you know. And it's a bit the same in the network. So correlation can somehow help, but it's not at all a good methodology to be sure that of your root cause analysis. And finally, another problem is that a lot of the data that we collect are coming from individual equipment. But what we discovered, I would say, with new methodology for the last 2-3 years, is that actually you learn more about the relation between equipment than really what is extracted individually by a specific equipment. And so we need to, let's say, analyze the whole system together with all the relation between the system, including with a multi-domain approach. I mean, historically, you had guys operating the transport network, other people operating the enterprise network, other people operating the radio access network, the core network, and so on, kind of in silo. And really, with the complexity that is increasing, it's not an approach that is sustainable. And now we need an approach that put kind of all the system together, analyze the relationship, and this is really the core of what we are doing with AWS. So with that, I give the remote control to Imen.
Thank you, Olivier. So as Olivier was mentioning, correlation is not causation. And the network dependencies, it means how the network nodes are connected together, were lost in the previous decade into a lot of tabular data. So instead of keep going with anomaly detection, aggregation that are static, and a lot of subject matter expert rule to put into a rule engine and then keep moving with those approaches since years, we stepped back and redefined the problem differently. So our mindset here is to say we need to think the network data right. So network data, it's not a tabular data only, it's not, let's say, unconnected data. So it is a connected data that it's covering, going through, for example, radio access network, transport, core network, and also to the user home network. So how we are doing this? So if you are working in the network domain, I don't need to convince you that the network is a graph. But if you are not from the network domain, let me give you an example. I am a user, I have my phone, which is connected into a cell. The cell is connected into a mobility manager to capture where I am in terms of location. And then this mobility manager is served by routers. It is connected to other databases where my profile is described. So all the network nodes are connected together, and they are connected through what we call network interfaces. So the network interfaces, basically, you can measure the latency, the jitter. You are measuring how this link is doing so that your call or your streaming is doing well. So all those measurements, they can have alarms. You have, for example, degradation in your call or degradation in what you are having in the service that you are using. So this is basically a very simple example of a mobile network, so where you can see the different nodes in the network, and the link in between are the network interfaces that are called edges in the graph domain. So basically here you can see that you can have persons, you can have databases, you can have routers, you can have base station. So by definition, the network as a graph, it's called heterogeneous graph. So heterogeneous graph, it means the network nodes are all different. They can be human, again, router, databases, etc. And the other criteria is that the network is evolving over time. So you can have new nodes. When moving from 4G to 5G, we have new nodes. Moving from 5G to the called 6G, we will have new technology to be added in the network. So this is from a topological perspective, it is changing over time. But also each node is having properties that are the measurement, the KPIs, and the alarms. Those are also evolving over time and changing over time. And as Olivier was mentioning, it's not 1 or 2 KPI, it's thousands of KPI per node. So today there was databases for KPIs, databases for alarms, and the topology and the inventories, and the dependencies were completely lost when we are doing AI. So keep in mind that the network is heterogeneous and temporal graph. So this is the first foundational question that we are having here as part of our approach. Now, how we are graph, how we are using graph for the root cause analysis, or why the graph is important for the root cause analysis. So basically, again, we come back to the concept. If you Google like correlation, it's not causation, you will see that this is a topic since 20 years that everyone is trying to solve. So here we are revisiting this with the graph technologies to bring the connection together in the network. So this is the first component. We are leveraging the connection that are natively existing between the network node across the different network segments. The second part is that we are capturing, this is the innovation we put in place, we are capturing the temporal changes, because if you don't capture the temporal changes of the network, you will miss the current state, you will miss the current exact behavior of your network node into a geographical area. And the last part, the graph techniques or the graph as an approach is meant to scale. It means it can go from a couple of nodes to billions of nodes, and then you can capture all the connection there. And the advantage here of having this built into AWS, it's our techniques that are optimized to run in milliseconds with billions of nodes in the graph. And here you can visit, for example, Amazon Neptune Analytics, and the latest advances on the graph rack that were announced this morning by Swam. So the other question that, okay, now you have your network represented as a graph, you have your millions of nodes that are represented there. You can go from a simple network node into also very low granularity, like representing even the card, the node, and other, for example, configuration files. You can go to whatever granularity that you would like to have. And here we help Orange to have a trade-off between what is needed to be modeled to get into the root cause analysis without overloading the graph and having a lot of noise. That's very important also in supporting the modeling part. So once you have the graph as a database with all the network nodes represented, how you will, which technique you are going to use on top of this graph. So once you have this graph representation in a digital format into a machine-readable format, which we call digital twin, you need, let's say, optimize a technique to traverse that graph. You want to know, for example, how to predict for example, I take an example of the network domain. You want to predict the congestion in the cellular network. Today, you will use classical machine learning to detect anomalies. You will have a lot of noise when you are detecting the anomalies, because you are not taking into account, for example, the cell interference. You are not taking the distances between the cell. Those information could be simply represented into your graph. And to capture them, if you use graph neural network, which is just simply deep learning on graphs, you can do forecasting, you can do anomaly detection, but in the same time, you are feeding to the machine learning the dependencies. And this is a game changer for the network domain. The other part is the scale. Of course, you want techniques of deep learning that can scale to millions of nodes, that can scale to changing network domain and network representation. And this is what Neptune machine learning, which is the layer that it's with built-in models. All of them are open source, optimized by AWS and running with Amazon Neptune layer within the Amazon Neptune graph database. They are built in for you to use and to run for the different use cases, again, for example, regression, classification, clustering of graphs, etc. The last part is that if you are working also on the network domain, you know that there are many, let's say, customization that are needed. So we are here having SageMaker to help you use, for example, an open source graph neural network, which are from the family of what we call spatiotemporal graph neural network that capture the topology and also the temporal aspect. And you can use those models and ingest them into a SageMaker platform, and then you will use all the MLOps feature, the evaluation of the model, the different criteria for running this into production. So you have different services and different support to run graph techniques, graph neural network techniques on AWS, and specifically for the network domain and use cases. So remember here we have the first part is the graph modeling, the second part is the graph machine learning, and the most important part is the graph analytics. So what is the difference between graph neural network and graph analytics? The graph analytics are not necessarily machine learning models, so you don't need to train. Those are kind of statistics or probabilistical model that will run into the graph, traverse your graph, and bring to you the insights. So example, you will know what is the most important node. You will know what is the most important network node connected to the others. You will be able to create communities in your network. So for example, as Olivier was mentioning about the traffic, you can, for example, cluster your network per traffic pattern. You can cluster your network by the volume of alarm occurring in different geographical area, and you can have different insights in a couple of seconds. So this was made GA last year in last reInvent. So here it's all also open source models, so you know the models, you know what you are running, there is a lot of transparency there, and it is all optimized to run in milliseconds for billions of nodes. So we have 3 components that are the foundational aspect of our approach: the graph modeling, the graph machine learning, and the graph analytics. Now, with those foundational components, we build the network digital twin for Orange, for Mass Orange, with the network operational team and the support of Olivier teams. Those are the features. Before going to the feature, I want to remind what are the problems we are solving. We are solving that the inventories are not complete today, the network inventories, they are missing information. We are breaking the silo between the RAN, the core, the transport, and the microwave network, because we need the data to be seen end-to-end by the machine learning and by the graph analytics. And we are scoring the different nodes to find out and isolate the problem in the network in a couple of seconds. So basically, the feature, in summary, we will show you the end-to-end topology across 3 network domains today from different network vendors. So we break the silo also in terms of data model and in terms of differences between the syntax. We also will show you the temporal network graph. So this is one of the first worldwide representation of how your network is moving over time with the differences that are changing in terms of KPIs, occurrences of alarms, and other. And the last part, of course, the generative AI is consuming all those insights. So the generative AI is connected to the graph analytics endpoint. It is connected to the graph database. It is connected to the graph ML and consuming those insights to deliver one consolidated report to the network operational team. So with that, let's see this in action. So here, the idea is to show you those features with the video demo that is running on Pontevedra region and on Mass Orange in Spain. So we worked on one region to capture all the difference in that region and identify the RCA. So this is how it looks like, the UI of the tool. First of all, this is how a network operational team will navigate, will use this. The first feature is the Network Topology Explorer. So Graph Explorer is already available in Neptune, our AWS Amazon database, where you can visualize your network topology and identify the insights. So here, for example, the network operational team will select one node, which is a wireless device. It can, in a couple of flicks, unfold and find that this device, which is from the wireless domain, is connected into an aggregation router from the transport domain. So this is going beyond the silos that they used to have between the network tools and the OSSs there. So here it is bringing together those views. And you see, each time it is clicking on that, it is unfolding and discovering the topology. And you can see that it is going from the microwave to the transport and to the radio access network. Now, the other feature is that the graph, when you are modeling as a graph, there are different languages to access the graphs. There are, for example, OpenCipher, Gremlin, or RDF. The network team are not necessarily using those languages in general. So this is why here generative AI is very useful. They will navigate the graph. They will extract the insights from the graph without them going and to learn those languages to extract the information from the graph. So here you can see that it was showing all the differences alarm from that graph. The other feature, which is the core of the topic, so here, each of the scenario that you see here is taking 7 hours plus for the network operational team to find the root cause. So here we are showing you the example number 3. So these are sequences of alarm. In a couple of seconds, you will see that the graph analytics calculated the score. So what does it mean? It means the algorithm was seeing all the nodes with alarms and telling you all the ones that are in purple are not the problem. It is finding the problem, which is the microwave device in yellow in a couple of seconds. The blue ones are the radio network nodes that are impacted, and this is the root cause. So this is as simple and as fast as you see it here. This example was taking 7 hours in our team to be found, and here in a couple of seconds, the algorithm spot this directly. So all alarm in the RAN, but the problem is coming from the microwave, and the algorithm was able to denoise the other alarm and point the problem directly. So generative AI is triggered automatically once this calculation is done to share the report. So here, if you can check the report, that it took just a couple of seconds to read, you can see that it is navigating the heartbeat alarm that are appearing in the RAN. It is telling you when those alarms appeared, and it is bringing to you the root cause, which is completely from another domain. So today, why they were spending hours? Because they have tools for the microwave, tools for the RAN, tools for the core, and they need to navigate those tools separately. There is nothing bringing the dependency in between. So this is the power of connecting everything together. This is a more complex scenario, and you will see here the list of alarms. So we're intentionally showing the list of alarms. You can see how different are those alarms, and this is only a subset of what is occurring. So when you look at that, it's impossible to find the root cause. Again, here, the algorithm take all those alarms, map them into the topology, and run the graph analytics algorithm. And you can see that the problem here is the router in yellow. All the things around in green and in blue are the ones that are mostly impacted, and all the others that are far in the graph are completely just noise and not really impacted by the problem. So here again, the root cause is identified. This is the router that is causing the problem into the network and having trouble for the radio access network node. And then the model can, of course, as Olivier was mentioning, can go until the recommendation of what can be done in the network and proposing how to troubleshoot. So this is basically the difference between rule-based and graph analytics. When you capture the dependencies, how you can go into the root cause quickly. So now the last feature to show you here is this is, for example, the view of the Pontevedra subset of the nodes that are running. And running by means this is the topology evolving over time. The KPIs, for example, we will zoom on the place where you have the red links. This is to show you that this is a red link. Now you have your graph analytics. You click on the button, you know what is the root cause in a couple of seconds. So you go from a lot of, like, say, screen with a lot of KPIs to follow a threshold into a temporal topology that it's telling you where the problem is, and you are augmenting this with generative AI and graph techniques. So what is behind the scene? You know, behind this magic, there is a workflow, there is a lot of data preparation, there is a data pipeline, which is the graph data pipeline in this use case. So basically here, of course, we worked with Mass Orange teams and Olivier teams to, first of all, understand the logic. What is the granularity that they want to identify and model in their network? And this is, of course, extensible if they need to have more network node modeled. The first part is modeling the network topology, automating this. This means that each time you have the data coming from the network, this is all automated and it will be represented as a graph in the graph database directly. So this is kind of topology discovery automation, capturing the changes over time. The second step, which is very important, is you need to infer the missing links because, again, the network inventories, and if you're in the network domain, you know that those inventories are not complete. So you need to infer the missing links. And here we have techniques like link prediction, which is a machine learning model that is graph machine learning model or graph neural network model built in Amazon Neptune ML that you can trigger, and it will infer for you the missing links to complement your topology. So once you finish step 1 and 2, now you have, let's say, an end-to-end topology completed, and of course you keep upgrading and verifying this over time. This is a data pipeline, so it means it is always changing. Now you move to the third part, which is graph analytics from the Neptune Analytics engine and SageMaker for the graph neural network and the generative AI accessing to all those insights. Another view, which is more the architecture from data-driven perspective. So this is a high-level view of the architecture. And if you want more information, please reach out. So let me describe it per block to simplify the view. So the first part is the data preparation. The network data is heterogeneous. So you have XML files, you have YAML files, you have CSVs, you have tabular data and structured and non-structured data, and you need to make sense of all of this because all of this is connected at the end of the day. So to build the graph model, we first start by a lot of data engineering that we automated and put in place to transform raw data into graph format, and from there build all the analysis. That's the first block. The first block is the data preparation. The second block is the intelligence. And the intelligence, we are combining graph neural network and graph analytics for extracting the insights from the graph topology and all the alarm and KPIs that were mapped into it. And the last block here is the construction of what we call the network knowledge. It means your graph database with all the temporal data that is connected to each and every node. and of course the generative AI to access this information and make sense for the root cause analysis, for the change management. It is actually for what if scenario and can work also for IT network. For the visualization of the temporal knowledge graph, we were using Tom Sawyer, which is a partner of AWS, to visualize this over time and connect this directly to the AWS database. Now, let Olivier talk about the benefit of how this approach helped them in the root cause analysis.
Thank you, Iman. Thank you, Iman. It was really brilliant. And it's really a project that is fully in my heart. So I'm very happy to be there today. So just before wrapping up, a couple of, let's say, summary of the benefits that we get with this project. The first one is obviously the time to root cause analysis, what we call the time to root cause analysis, which is a proxy of the time to remediation, because a lot of the remediation could be short, depending on what is to do. But for root cause analysis, in the example that Iman showed, in the two examples, we were about several hours, order of magnitude. It was 7 and 9 hours, I think, because we made really the exercise to do that manually. And the system that Iman presented has been successfully capable to deliver the right root cause analysis in a couple of seconds, maybe in 10 seconds, 20 seconds. It's not really important. What you should have in mind is we come from hours to seconds. So this is the first benefit. Another benefit that could be a side benefit, but it's not, is that this system is also capable to deliver the end-to-end multi-layer topology of the network. And again, the way networks are done, the way what we call OSS, so the IT system managing the network is still very siloed, which means that it's difficult to have the end-to-end view of let's say the full network. And here in this case, we have done the job with the transport network and with the radio access network combined together, and building the capability to do root cause analysis on this whole system. In the future, we could add other domains. And obviously, the last benefit in this summary is the alarm management. Again, we are talking about thousands of alarms every day. And this system, including the add of Gen AI to, let's say, create the automated report, and also drill down, because you can also raise a question with the Gen AI about an incident, and if you don't have the complete information in the report, even with people not capable or not skilled with like SQL or other technology to really dig in the database, the Gen AI that we put on top was capable to both deliver the report and interact with the network operation teams. So it's not done. We still have a lot of things to do. It's a project that maybe I will be happy to come back next year to give the last word about it. So the first thing that we need to do is to make it really live, in a sense, because we have done this as an experiment to make it fast. We have used extraction of it's real network data, obviously, but it's based on extraction. So this means that the full benefit, in order to get it, you need to have live pipeline, because what you want is to detect an anomaly and to make the root cause a couple of minutes maximum after the incident happened. And obviously, if you rely on batch, then you don't have this benefit. So this is the first thing on our table to do to make it live. The second thing that we need to work on is to scale to a full country. So currently, as Iman said, that we've used the data from a region that is called Pontevedra in Spain. And we should go to, let's say, multiple cities, multiple regions, or even the full country. And we also need to continue to work on this spatio-temporal graph neural network. We have a very good basis. It's working very well. But with going live and also increasing the scale, we will probably fall on some let's say, new issues that maybe we did not have yet on this project. And it will be the opportunity really to make this tooling even better than it is today. Yeah, I think that's it. So
thank you.
Maybe a couple of...
I just want to say thank you. Thank you to the Orange team for all the work, Eamon, over the last year, coming together, bringing this entire collaboration to life, from data management perspective, network topology discovery perspective, bringing together graph attention neural networks, and then making it real with generative AI. I think this is the proof is in the pudding, what we saw. Scaling these primitives that the cloud architecture from AWS provides on an operator that is leaning in to the vision of autonomous networks is how I think we can make the future real. So thank you. Thank you so much. Appreciate it.